Hello and welcome back to Calculus 3, section 11.7, motion in space. Physics, right? So we start by peeking at the 2D first, and we realize that on the xy plane you might have a function given as y equals, say, t squared, and this would be a path. And I told you in Calc 3 you should put this on the floor and step on it and walk on it. So what you see now displayed is something that would be on the ground, and we'll be building three-dimensional objects upon it. So when you had something like this was the function, let's say y of t equals t squared. That was the position. And at any time t that you give me, I will give you a location in space, right? But then what I'm going to do is I'm going to say I can take the derivative, and that will give me a velocity function, which actually measures how fast the object is moving and in which direction. And that one was v of t, and it was, let's say, this way, and there was tangential component, and then we have a of t, which is acceleration, which is perpendicular to velocity, and if it's happening on a curve, it is pointed towards the center. So now these concepts from 2D will transfer to 3D, where our 3D motion is happening along the R, our vector valued function that shows position in space. So I'm going to have some kind of curve in space, and then I'm going to say this is a vector R, and then at that point, let's say in blue, I'm going to have velocity again in terms of t. It's another vector valued function, and then I'm going to have acceleration. Let's say it goes this way. So this is going to happen at any point. So I can draw another set, let's say here, and then velocity maybe goes this way, and then acceleration, let's say there. These are all vectors. So all of this stuff translates from your 2D into the 3D at the same way. Now, calculation-wise, sorry to disappoint, but I have nothing new. Your position now is going to be r of t. You already know what it is, how it looks like, and all of that stuff. So f of t, g of t, and h of t. Velocity is going to be v of t, which is actually r prime of t, which is f prime. I'm just lazy to write this of t. You know it's of t. And we have acceleration, which is a of t, which is the first derivative of velocity, which is the second derivative of position, which is F double prime, G double prime, H double, all of t. I'm just skipping on that. Off of velocity, what do I get? From velocity, what else can I get? Speed. And what speed? Yes, in this case, we'll say magnitude, right? So, prime squared plus G prime squared plus H prime squared. So that's speed. Yes.
You have the position, velocity, and acceleration with respect to t. That's
Everything is respect to time.
that t is from if that's the beginning type of time.
Parameter, yep.
Okay.
You don't have to have time to be the parameter, right? But we usually have time to be the parameter. You can parametricize over an angle or something, theta. So when you write parametric set of equations for circle, you can say, so for circle, there we go, circle, and you can say that x is equal to r cosine theta, r sine theta for, but you can also use r cosine t and r sine t. So which parameter are you choosing? Well, one is going to say it's time that takes you to draw it out. The other one is the angle. It doesn't matter. So it's a universal parameter. So we are using t. In mathematics, we don't actually have to limit ourselves to think in terms of the physical concepts, actually, things that we actually see and touch. And we can just say it could be anything. You can say elephants. It doesn't really matter. In physical sense, it has really absurd meaning to say, yeah, it's done in terms of elephants, because it's not, right? We understand what the elephant is. But the trick is that what you are understanding here, that there is a collection of three outputs that are provided by the single common input. And eventually, you will realize that mathematics is broken into these kind of pieces where you have single input, single output, multiple output, single input, and all of that kind of stuff. So in this case, yes, this is that same t. This is that same t. And for purposes of just understanding it on the, I would say, easiest level is just to say, yeah, that's time. Because time is common. All right, so they do talk about the circle. I practiced the entire break. I can draw perfect circles, guys. Look at that. Right? Years of practice. Well, I haven't practiced that yet. But eventually. So we have the parametrization for this as x equals r cosine. What do you want this radius to be over here? Gesundheit. I know. If you picked any other number, I pretty much wouldn't be able to say that, so thank you. So 2 cosine t, or theta, whatever, y equals 2 sine t. So here, I'll write it in blood over here. This is parametrization. That's from chapter 10. Now, what I'm going to do is I'm going to transform that into Calc3 language by writing it as R of t is equal to spiky bracket 2 cosine t. There we go. 2 sine t, and put it in this form. So this is on a 2D surface. It is a path. If you are to walk on it, you will be going in circles. But then you actually do that. Go to Somerville Circle.
No.
You can actually get a ticket for that, so don't. But
The part of Somerville Circle is in Somerville.
that's true too. So now we can find the velocity. Now, let me first show something really interesting. You guys hopefully remember that because you have only two dimensions, x and a y, but you are introducing a third variable, which is t. In math language, that's just a third variable, that's a third dimension. So you actually are talking about a two-dimensional concept, but utilizing 3D, which means that you have 1 degree of freedom that can be used for something. And in that case, it's the orientation of the curve. So the motion on this curve, the way the curve appears, is going to be counterclockwise. And we can show that by simply computing this r at a few of these locations. So you can compute r at time equals 0. So if you compute r at 0, what you get is a vector 2, 0. Right? Because cosine of 0 is 1. 2 times 1 is 2. And then sine of 0 is 0. 2 times 0 is 0. So 2, 0. Vector 2, 0 is going to look like this. That's vector 2, 0. Well, actually, the vector 2, 0 starts at the origin and goes up to 2. But remember, they are free to move in space. So this vector and this vector will be the same. And the reason why I'm putting it there is because I will be walking on this line. Right? I'm not walking there. I'm walking on the circumference of the circle. So I'm just going to move this to the location where the time is 0. Everything starts here. And you can see that this motion is kind of saying, well, looks like we're going to go up. Now you can try at time equal pi over 2. Yeesh. Time equal pi over 2. How much is that? Yeah, it is 0, 2. But how much is the time pi over 2? It's roughly what? It's midnight, right?
Why do you write it? I know you like went in depth into the difference between like the and like the bracket, but why are we not using like the parentheses one right now?
Because these are vectors.
Oh, I just didn't have the arrow.
You can just say put arrow. You don't have to.
No.
You don't have to go that way.
No, really, I didn't know. Thank you.
Oh,
I was just like,
just naturally.
Why is the one going up when the 2 is in x and the other one is, why does it look like it's split?
Well, at this point here, which is pi over 2 point on top, right, on the y-axis, we have to draw the vector 0, 2. 0,
Doesn't that look like it's going up?
0, yeah. Hold on. When I put pi over 2 is 0. No, 0, 2. It was good.
But why isn't that it going negative?
So how are you guys? You good? All right, perfect. Yeah. So R0 is the radius that shows the location where the point is. There we go. So that's a 2, 0 vector. Then 0, 2 vector is this one which shows the location. And then you'll have the other ones as well. I'm not going to calculate them. There's no need. There we go. Much better. Now we switch to blue for velocity vector. Negative 2 sine t, 2 cosine t. And if we are to compute some of these velocities, velocity at 0 is negative 2, no, 0, 2. 0, 2. So 0, 2 is the vector that I had before. There we go. That's a velocity vector. And then if you compute velocity at pi over 2, you will get what? Negative 2, 0, which is this one. And then you're going to have this one and that one. Okay. So the blue are velocities. So when you're looking at this, you see that the motion is spinning, right, counterclockwise. And then acceleration, another derivative. So we take one more derivative, and if we are to compute those, we're going to get acceleration vectors that point inward. Like that. Everything is color-coded, should be easy to follow. So, black vectors are the ones that are getting us to reach every single point on a circumference because that is the position vector. It shows where the particle is. So you have a particle, or the elephant, or whatever, walking in a circle, right there, or going in a circle. And at any time t, you are able to find where their particle is because you have the function for it. In terms of velocities, the derivative of the r is velocity. You take the independent derivatives. When you compute them, you get these vectors that show that the motion is this way, which is counterclockwise. And that's technically what, yes?
If I wanted to make the elephant run faster, what would I?
Scary.
How would I change the equation? Could I say 2 cosine 2t? Or 2
But I
cosine
take a coefficient from the function.
sine 2t?
Bigger coefficients change the radius. And your answer was?
Yeah. You use different colors.
Which is true, because the wavelength is actually the same. So yes, you will actually change the period.
Mm-hmm.
If you change the period, you can speed or slow down the process. If you change the amplitude, you make the circle larger or smaller. Those are the two things that you can adjust. Yes?
So, you know how you said t could be either like time or
Angle.
or whatever? Could you make t instead like another coordinate, like based on where it's moving on like the z coordinate.
But see, the understanding chapter 10, the part of understanding chapter 10 is to understand that parameter t is not a coordinate. The x and a y are locations on a 2D. X, Y, Z are locations on a 2D space. T is the common value that they will all use to kind of line up. There is atomic clock, and then all of the cell phone companies dip there and send signals to your phones so we all have common time. That would be that T, right? Where all of us would be different variables. All right? So the idea over here with this T is you're not making that a new dimension in terms of partial dimension like x, y, z, because you can do that with x, y, z. This T over here drives the entire system. So what parametric equations do is they separate dimensions. You have one equation for x dimension, one equation for y dimension, and later one equation for z dimension, and they can all be put together back into a single equation x, y, z by eliminating parameter t by plugging in one into another. So technically, you choose whether you want to describe your shape with parametric equations or without parametric equations. But with parametric equations, obviously, you have more power because remember the circle is not a function, so you can't integrate. You can differentiate with implicit, but it's pain. Where if you write in the parametric equations, it becomes, in terms of functions, easy to deal with that. So t is not on the same level as x and y. It's a different region, right? It drives them in some sense. It drives them. Did it make any sense?
Yeah.
So if you are here at this point, you would be at, that would be at time pi over 4. So at time pi over 4, you can figure out x and a y, so it will be root 2, root 2. So this location over here would be root 2 or root 2 in coordinates as a location. But the time at which, particle reaches that point to kind of be at that point would be pi over 4. Now, pi over 4, again, that's radians. So pi over 4, you can actually think of it as time as well. Radians are kind of tricky. That's the unit that you want to use. It's a ratio of 2 inches divided by inches. So we'll talk much more about that when we deconstruct certain equations. Any other questions, concerns? No? Let's see what else. Just a quick question. What do we see between position and velocity and then velocity and acceleration? They're perpendicular. Yes, they're derivatives of each other. That's how you get them, but they are perpendicular. No, they're both correct. I was looking for actually perpendicular answer, but derivatives of each other, yeah, sure. And what do we know? Two vectors are perpendicular. The dot product is 0. So it's actually a theorem. for circular motion, which is this, that if you have the dot product is 0, velocity and position function are perpendicular to each other. So that comes right from the dot product. It's theorem, I don't know what is labeled. Let me just find it in the book somewhere.
I can
11.8 motion with constant r. So theorem 11.8, and it says that the dot product between position and velocity is 0 because they're perpendicular to each other. Good. All right. We can also go the other way. So if you have acceleration, we know that that's change in velocity over change in time. Now these are vectors, which means that we can find the velocity if we integrate acceleration in terms of time. Now, see, this is a cute way to write it, right? Because it's just velocity is integral of acceleration. Wow, we're done, right? But if you really want to write this in terms of the components, you would have to write everything. And then you can also get your position vector from there. So vector r, so that's just unwinding everything, is integral of velocity. And clearly you'll have your plus c. Now, talking about the parabolic motion and all of the formulas you learn in physics, we can easily put all of those formulas that you usually do separately in a single vector, because we have x components of motion, y components of motion, then x component of velocity, y component of velocity, and same for acceleration, x and y components. So we can put everything into a single vector. And you will recognize all, I hope, you will recognize all of these equations because you took physics. So velocity is going to be given, they say, u0, which is the x component, and then minus gt plus v0. So this is the v0 is going to be the distance in, the velocity in y direction, and then you have minus gt, which is deceleration or acceleration, deceleration due to gravity. And if you are to integrate this, you will get the formulas that you remember as the parabolic motion. So you will get the vector u0t, and you get negative 1/2 gt squared plus v0t plus whatever we're going to use here. well, plus c, vector c, which is constants. Now, how awesome is this? U0t, it shows that for the x component, and this is what you are memorizing, I know at least one person knows, that when you have the parabolic motion, let's do the experiment, right? That's why we love physics. Don't worry, I do this for a very long time. See? Parabolic motion. It was a parabola, and you can see that negative x squared, in this case t squared, so that's the negative t squared. And for the y component, clearly the y component, which is the one that goes up and down, is affected by gravity, affected by for which how fast I throw, and from which height I throw, whether it's 6 feet, 5 feet, 3 feet, and so on. And you can also see that the x component of that velocity is constant. The gravity does not affect forward or backward motion, just up and down. So they did summarize this in a textbook. So you've seen all of this already in your physics classes. Exactly. I know, we'll get to more interesting stuff quickly. Well, you won't be laughing then. That's the one. So an entire problem in physics where they would have the baseball ball that you go right and it goes. Yeah, crowds go crazy every time. Over nothing. You solve the whole problem by plugging into one vector right there.
Is this important?
I'm sorry?
Is this important?
That's why it's in red.
Okay.
The red box. They have the blue one. Would you like me to use the blue one they used in the book?
What about the pink highlighter?
That's insanely important.
Okay.
When I put something, I say like the most precious things are in pink.
Yeah.
I knew some was going. And then they're getting in the textbook to be very, very specific about the range and the time of the flight, the maximum height, all of the good things. You know that the maximum height can be computed when your velocity is equal to 0. Observe. Experiment number 2. Stop, and then comes back down, right? So how do I calculate maximum height? When this goes up, it has to actually, once it reaches the maximum height, it stops and then changes the direction. At that point, you see, I give initial velocity. If I don't give initial velocity, it just drops, right? So that's the difference between throwing something and dropping something. You usually drop things with 0 initial velocity. You never seen anyone drop things like that, right? That's not how you drop things. Like it's usually whoops, right? So it's lost. So the initial velocity is the one that makes things go up, and then the gravity. I said it was lost.
That's okay.
Now I feel bad, but I know it's going to pass very quickly. All right, I'm over it. So the initial velocity is the one that when you throw something, right, it makes it go up, but then the gravity is going to keep slowing it down, which is which is this part here. Oh, come on, pen. Oh. So this is the part. So you have the initial velocity of a throw, and then the minus gt is going to slow it down, and then it's going to stop. So when do you reach maximum height? You reach maximum height when this is equal to 0. Right? That's the velocity in the y direction equal to 0. So that's when it's maximum height. Maybe you should put this in your notes. That's when you find the maximum height. You will actually first calculate the time. You calculate the time at which you have the maximum height, and then you go into the height equation and you figure out how high that object is. There was some efficient sneezing there. One of them. Time of the flight, obviously, time of the flight is for the entire flight. You have the height to be 0, right? So this one is 0 at the beginning, at the end. So you find zeros of this polynomial. And that's what's, so beautiful about mathematics. It's just, you learn a few things and then they apply everywhere. So here's that parabola, and you see that the roots, maybe I shouldn't put the, let's put the y-axis somewhere else. So this is your time 1 and time 2, right? And your x1 and your x2. So when you solve this equation equal to 0, right, you will get, when you find times for which t is 0, you will know when did it hit the ground. Now usually, if you drop something from 6 feet, you start from there, right, you are going to get this negative nonsense value, but you know it started here. It's this one that you usually hunt for, because when you throw things, usually there, right? Because you threw something. All right, so that's that part. Sam, for the object to go the furthest, what was the angle? 45 degrees, yes, good. So if you throw something at 45, it's going to go the furthest it possibly can. So next time you try to throw something, protractor. Never leave the house without one. And then you have, if you don't want to think about things, in terms of a concept, maximum height occurs and maximum range occurs and so on. Oh, it's called an alternative approach, right? As I said, or don't. And now for 3D. For 3D, and I love it's done the same way in a textbook. It's technically what they say on a page and a half is good luck. All right, that's what it says. So page and a half of text that technically means good luck, because when you are talking about the motion in 3D and you want to try these physics equations, they don't work. All right, because in 2D is easy, right? In 2D is easy. But when you go to 3D, again, reference points, x-axis, y-axis, z-axis, stuff is all over the place, right? So you think about that if I put the x-axis on one wall, the y-axis on the other wall, and obviously z goes up, I can throw something 45 degrees or 37.8 degrees. So you have to, for 3D, you actually have to sit down and decompose this to the point where you can apply the two-dimensional equations. Anytime when I throw the object in 3D, the object will actually travel in 2D, right? So I was throwing object this way, which was along this wall, which is the x-axis, so call it x-axis, and then z-axis, so that's still 2D. All of these equations apply if I throw it this way, because the way I threw it and the axis are parallel, so mathematics applies that way. If I throw it this way, forward, again, I'm parallel with that one, so that's, let's say, y and z, perfect, right? Again, 2D. But what happens if I aim for mark and throw that way? You see that it's not along this wall, it's not along this wall, right? So you can't use the equations out of the box. But then you realize that whatever the vector is that connects us, which is going to be at angle to this, is going to, in that frame of reference, going to use these formulas. So it gets to be a little bit trickier to compute this. It's not impossible. It gets to be a little trickier. And usually when we take courses like statics and dynamics, you enjoy that kind of stuff, as long as you understand vectors and input and so on. They did one example to kind of show this kind of swing. Read it, see how it looks. I'll draw a situation. So 3D. I have X, I have Y, and I have Z. And then I throw something along this one at 30 degrees. So that would be I throw from the origin and goes like that and falls there. So along this line that is in XY plane, so along that line with z-axis up, our 2D equations apply, where the rotation of the coordinate system from linear algebra really helps with these kind of things. So I hope you will really pay attention in that class. Yes?
You're using like a projection of the trajectory work?
Oh my God, that would just make like 5 times worse. But yes,
Worse?
yes,
Okay.
sure, why not?
But that would be worse.
Yes. So they do show how to, it's important for a lot of calculations, guys, in engineering, a lot. You can have a boat. I mean, people are somewhat resistant now to the autonomous cars, but people don't even realize that, autonomous planes been around. You do still have a pilot who, occasionally shows up, right? But the trick is that when you're taking any of these flights now, nobody's driving that airplane is going on its own, all right? Because the pilot will never be able to match the calculational power and quickness of the machine. So this kind of calculation, you want to go down the x-axis, there is a crosswind. Same thing for ships. No one is sitting there, on the big wheel like that, and with spikes right around with a parrot on the saying "arr," right, for these cruise lines and so on. The thing is going, they know which direction it should go, and then when there are currents and winds and stuff, it kind of goes off of the axis, and they just correct the course for that ship. This is your C, right? And you're supposed to go that way, but you're going this way, so now we have to move it back, and so on. These kind of corrections are done by the computers, and adjusting the course is done by the computers. Not humans don't do that anymore. You get it, if it's a rough landing, then they go a little bit, and that's it. That's it. There are a few of these exercises to enjoy. What time do we end? Sorry? So what, we have 2 minutes and then another 28 after that. Okay. We have time. So we'll end this one, and we can take a look